Welcome, everyone, to another presentation here. We have the basics of accelerometer calibration. I am Patrick Timmons, and we're going to break this down here into, it looks like a two-part series. So this first part, we're going to talk about, generally speaking, what is calibration, why we're calibrating, what we do on the manufacturer side for accelerometer calibration, and eventually, second part, we're going to talk a little bit about transverse sensitivity and transverse motion. So, what is calibration? Well, there's this nice definition here from NCSLI, and I will actually read the screen here. Pardon me, this should be the only time this happens. Let me know if it's not. But we have a definition here for calibration as a property of a measurement result whereby the result can be related to a reference, typically through the SI, through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So it's a series of calibrations. You're documenting what is happening in each of those calibrations, and in most cases also reporting some sort of measurement uncertainty in there. So why are we calibrating? Well, for starters, when a manufacturer creates a sensor, like the one pictured down here below, it's a nice tri-shear accelerometer. When we make one of these, we have to calibrate from the start. This device is pretty much useless when it's manufactured without a calibration. It's a transducer. It transduces a physical phenomenon, in this case, acceleration for this accelerometer here. And it transduces that into an electrical quantity, voltage in the case of an ICP sensor. So we have some physical phenomenon, we want to measure it, we put this thing on here and it transduces that phenomenon into a voltage. And so with our data acquisition system, with our meter, whatever we're using, we can measure that voltage, and great, now we have a voltage. So ultimately, in your test, you're not really interested in volts, you're interested, in the case of acceleration again, in G's or meters per second squared. You want to know what is the acceleration of the device, the structure that you're testing. So that's where the calibration comes in. You want to generate a sensitivity factor for this transducer that relates the physical phenomenon to the electrical quantity. And that's often given as millivolts per meters per second squared or millivolts per G. In the case of a charge type accelerometer, it's going to be picocoulombs per G or picocoulombs per meters per second squared. It's a sensitivity factor of your calibration. So we have that. We can now get an output out of our sensor that is in the acceleration units. Great. So why are we recalibrating? We've got our value. We know what it does for this sensor. We should be good. Of course, things happen. We want to often check to make sure that over the lifetime of that accelerometer that it is still behaving the way that we expect it to, the way that it was originally calibrated from the manufacturer. So on the right there's a nice little picture of an accelerometer that's been through some things in its life. It's had some rough days, it's missing a couple of the weld caps on there. The base is a little bit bent and there's definite marring on some of the surfaces of that triax there. So those kind of two open faces, you can actually see two of the sensing elements for two of the axes in the triax. So that one obviously has been through a lot and it's pretty easy to see what's wrong with it. But oftentimes, even things like scratches, gouges, dents, or even internal damage that you just can't see happens to accelerometers throughout their lifetime. It depends on how they're handled and how they're used. The famous example I always like to give is, Joe, technician, is out there working on his system and he needs to pull these sensors off here to rearrange them. And without much training, someone tells him, hey, go up there and grab those. So Joe grabs a flathead screwdriver and uses it like a chisel and bangs on the bottom of the handle there to pop off an adhesively mounted accelerometer. And in almost all cases, that is going to gouge the bottom of the accelerometer and oftentimes the structure a little bit as well. But for the accelerometer, damage to the base is the #1 failure mode. It's going to change the frequency response characteristics of that sensor. So yeah, Joe, careful with the screwdriver. It's going to affect the results of the sensor over time. So take care of the accelerometer and you'll have consistent data there. If you don't know what's been happening to your accelerometers, or you need to know what's been happening to your accelerometers, this is where recalibration comes in. So it's going to be in the form of a reference sensitivity check in most cases, along with frequency response. So it's just assessing what is the sensitivity of that accelerometer at different frequencies. And we do this, of course, because we want to know what happens to it. And oftentimes here, the boring reasons I give is the because we have to reasons. That's the ISO 9001, an equality system that is going to dictate that you recalibrate your assets on some interval. It doesn't give that interval, it just says you have to recalibrate your assets. So because we have to, oftentimes ends up in an annual recalibration because that's how budget cycles work, and people just say, hey, here's 1 year, recalibrate it. And that works. Again, it's the not fun reason, the because we have to reason there. On the last one, I mentioned specifically 17025, the 2017 version for risk mitigation. There's new information in there that people are dealing with on risk. And so a lot of people in the quality realm are paying a lot more attention to the uncertainties that they have for their calibrations and what is the ultimate effect of that recalibration and the uncertainty of that recalibration on the risk that they have in their process, in their measurements. So there's more scrutiny there. So pay attention to uncertainties, not just getting a piece of paper with a stamp on it. So we'll talk a little bit more about uncertainties here in part 2. What is accelerometer calibration? I like this slide. This is a good one. On the right-hand side here, we have a nice image of a specification sheet for a PCB 353B04. It's a uniaxial accelerometer, pretty standard measurement type Excel. And it has a bunch of specs on there. And from the manufacturer, you oftentimes have a cal sheet or multiple cal sheets that define what the performance of the sensor is. So the first couple on there that are called out pretty clearly: reference sensitivity and frequency response. These two are the most important calibration items that we have. And reference frequency, or reference sensitivity rather, is the kind of the main one. That's the value that you're going to have on a sticker for a sensor. And it's going to be oftentimes what you put into your data acquisition system as a sensitivity factor. And it's really what's going to matter for your system. We also have on here frequency response. Those two are highlighted in red because I mentioned those as the two important ones in the system. Frequency response is going to be the thing that is going to catch errors or issues that you'll have with your sensor. So pay attention also to frequency response. Last few in there, resonant frequency, linearity, transfer sensitivity. We have a couple on the bottom there, output bias or ZMO voltage, zero measurement offset voltage. Those are electrical quantities, along with time constant, which is a kind of electromechanical quality that you can get with a flip test on certain Excel. So they're kind of in order of importance or in order of frequency that we typically see these recalibrated for. But we'll go down through each of these and kind of break them down and tell you what they are. So the first one here, most important, reference sensitivity. It is on the bottom right there, my favorite set of equations. I know everyone has a favorite set of equations. This one's mine. It's wonderful. It is very simple. It is A equals A. The acceleration of your test article equals your acceleration of your reference. So in a back-to-back calibration, you have two accelerometers mounted on top of each other. On the bottom there is your standard accelerometer or reference accelerometer. And on the top, you have the accelerometer to be calibrated, or your sensor under test, device under test. So with that basic equation, A equals A, you make that one assumption that the acceleration that both of those items see is the same. They're back to back. They're seeing the same motion. You can break it down into terms of voltages and sensitivities of those two sensors. And so you have your V and your S, and your V and your S, and you can solve that equation down there for S sub A. And that is, what is the sensitivity of your test accelerometer? What is your sensitivity of your sensor under test or device under test? And to the right of that value is what is going on when your sensor is recalibrated. It is a ratio of two voltages there. The voltage that you get off of your test sensor, the voltage you get off your reference, multiplied by the known sensitivity of your reference accelerometer. So your reference accelerometer is ultimately calibrated through a traceability chain to laser primary. And so that S sub ref there is just a known sensitivity for that reference accelerometer. And in your calibration system, really all you're doing is gathering two voltages, one from each of your sensor, and computing this equation here. So in this type of configuration, you're using a shaker. This could be pretty much the same setup you'd be using for a laser primary system, only without that reference, you'd have a laser primary reference. And this reference sensitivity typically happens at 80 hertz, 100 hertz, 159.2. Some people round that up to 160 hertz. This is what's known as the reference frequency. So at a certain frequency that we pick, we determine what is the sensitivity of our test sensor. And that frequency of reference sensitivity is often based on the manufacturer's specification sheet. So whatever they have on there for how they're defining their sensitivity and its tolerance bands, it'll be based around some frequency. Typically in the States you'll see 100 hertz, and in Europe you'll often see 159.2. That is an interesting number, 159.2. It's strangely rounded to a decimal point and not really an equal number. It doesn't end in a zero. And so people are often confused, wondering why that number. Well, in Europe, of course, line power is 50 hertz. So 100 hertz is going to be the first harmonic. And sometimes, depending on your calibration system, can cause issues, or at least higher uncertainty at 100 hertz. So countries using 50 hertz wanted to use a different frequency, so they chose 159.2 hertz, which is conveniently a frequency where you can multiply between displacement, velocity, and acceleration by a factor of 10. So it's an easy point to know the different types of accelerations between, or types of displacements, velocities, or accelerations. So something that a lot of people have used is something like this calibrator here. And this is a calibrator that can define the sensitivity at a single frequency. And typically they're handheld, they're battery powered, and they operate at a fixed acceleration and a fixed frequency in most cases. Some of them have a few switches to change that frequency around, but most of the time you're using it at a single frequency and getting an output acceleration. These guys are really handy if you are setting up a series of test equipment. You have different data acquisition systems, you have different signal conditionings, you have gain in your system at certain points. It's often used as a sanity check, one of these guys here, to see if your channel is in fact connected to the right cable, to the right signal conditioner, with the right gain, ultimately back to the data acquisition system with the correct sensitivity factor entered in for that channel, so that the measurements that you're taking are accurate. A lot of times there'll be something dumb that happens, like a conditioner might have a gain setting set to 10x instead of 1x. And so you'll do this quick check, you'll put your accelerometer on a handheld calibrator, and it'll shake at 1G 100 Hertz. And back in your control system, back in your data acquisition system, you'll see 10 Gs. So 10 times higher than you expect. And it's a very easy thing to do to run back through that and chase down your conditioner that has a gain setting of 10x. You can also check things like, is the sensitivity entered in correctly, or are the cables swapped around? So on site, these are great tools to use to check that your system is working correctly. A lot of people ask, is it a calibration though? Can I use this with my data acquisition to make a calibration value for our sensor? You see at the top there, we call it a check, a handheld check. So the answer is kind of no. Oftentimes, the delineation that we have between what we call a check and what we call a calibration is whether or not that calibration is including an uncertainty budget. So some sort of analysis of what is the performance of my components in gathering the data from my units? What is the transverse motion of my calibrator? And with a handheld calibrator, I have never seen someone do that. So it's not something that people do frequently. It's kind of a quick and easy mode of checking the system is functional. So we often call this a handheld check. If you wanted to, component-wise, there is a shaker in that calibrator. It is controlled by a reference transducer internally. You could generate a frequency response or an uncertainty budget for that single frequency with this type of calibrator. If you wanted, though, to do that frequency response, you would use something like a portable vibration calibrator. So this is like a step up from a handheld calibrator. It's still portable. It has a little handle on it. You can bring it around from point to point and do that same type of field check where you measure an entire measurement chain back to a data acquisition system. A simple version of this is often used in the industrial world where you're doing condition monitoring on a pump or a motor, something that is vibrating that you want to make sure is not vibrating too hard, is not having a component failure. You can look at maintenance intervals for these type of heavy equipments to see if you need to change out a bearing or something in the system. And monitoring acceleration over time is a good way to do that. You run into that same issue though, has someone messed with the settings in the system as far as sensitivity? Have they changed a gain on the system at all? And are we getting the correct alert and alarm that we expect on our system? So you can use a portable calibrator like this to tune not only the amplitude but also the frequency to a frequency of interest for your system, and slowly increase that amplitude until you reach a level where you should expect an alert to be reported back on your system, or all the way up to a level where you would see an alarm back on your system. and you can radio into a different operator to confirm that at the time that you're setting these settings out in the plant floor, they're actually seeing what they expect back on that system. So it's an upgraded version of that, and more often these days, portable calibrators like this include more of an analysis of uncertainty. There's versions of these that can take that output signal from the test transducer and actually, instead of running it all the way back to a station, just run it right back into the portable calibrator, and you effectively have just a shaker with two inputs. So you can measure those two V's, the two voltages, the one from the reference internally and the voltage from the test sensor, and get out a calibration value at different frequencies for a unit like this. So there's more options for this type of calibrator. So overall, why are we recalibrating? Why are we doing this? This is a great example of actual data that we took on one of our rental assets, accelerometers. And in the green there, you can see the original data set. So this is not quite a manufacturer's calibration, but maybe a few years after. We've had it in a rental pool. Pulled one of those data sets here, and that's what it should look like for this specific accelerometer. We got it back from a job, and all of a sudden its frequency response became the blue curve there. So something definitely happened to this accelerometer, and funny enough, it's actually the one that I had pictured originally there. It's the one that had huge amounts of damage to the outside. It still worked, crazy enough. Didn't have any hermetic seal on the elements at all, but it actually gave an output. And as you can see though, if we had thrown the tolerance bands on here, it actually would have failed a manufacturer's frequency response band. So its sensitivity changed with respect to frequency too much, because the resonant frequency of the sensor had actually been shifted all the way down into the usable range. So we have a huge resonance where we expect to normally be using this sensor. So if you look at 100 Hertz though, the values are almost on top of each other. So if you're using one of those handheld calibrators to get a sensitivity at 100 Hertz, and you're saying, hey, the sensor is calibrated, it's great. The other big thing in the system really is doing this full frequency response check. This is where you're oftentimes going to see issues with an accelerometer, is checking through its frequency range to see if that resonant frequency has shifted down into your data set. And if you did a frequency response on this sensor, you would see the fact that it is failing a frequency response band. So that's why I highlighted those first two items in red, the reference sensitivity and frequency response. These are the two checks we typically like to do for a sensor. And here's a nice visualization of that. It is the frequency response of an accelerometer in red there, all the way up to the mounted resonant frequency. If your sensor is damped or gas damped, it is going to roll off slowly at high frequency. But pretty much every other accelerometer is going to have this resonant peak in it. And if you look at a manufacturer's spec sheet, you'll often see frequency response defined as a 5% limit, a 10% limit, or a 3 dB limit. And why do we choose these values? Are they important? Why not choose 20% or some other percentage there? They just happen to be three values that correspond to a fraction of that mounted resonance. So 20% of the mounted resonant frequency is oftentimes very close to a 5% limit. So we set these three values on a spec sheet for a sensor, and you can evaluate them by doing a frequency response check. Oftentimes you get a nice little curve like this. This is a high frequency check, starting at, I think all the way up there at 20 kilohertz down to 5 hertz. This is a typical range that we do for a high frequency shaker. You can see though here at these very low frequencies, the tolerance bands are still there, but we don't have data. If we wanted to go lower in frequency, we could use like a shaker on the right there, a low frequency shaker that has a much longer stroke to get more output out of the sensor, and test that sensor all the way down to 0.5 hertz or 0.1 hertz in the case of an optical encoder based low frequency shaker there. So this, again, it's the tolerance bands that you'll be checking against. The low frequency is quite important for ICP in looking at what is the low frequency electrical characteristic of that sensor. How does it roll off due to those ICP electronics? And kind of finally I'll talk about here is, why do people get a high frequency calibration? Why do they get a low frequency calibration? Should I be getting both? It really depends on what you're interested in, what type of testing you're doing. If you are testing windmills and you're really interested in the accuracy of that low frequency data, what's happening at 1 hertz on my structure, people opt for low frequency calibrations in that case. They'll maybe get a high frequency and a low frequency. And it's usually defined by the calibration code. There'll be a specific call out for the frequency range, and you can elect to get a low frequency. On the other case, there's people who really don't mess with data below 20 hertz, for example. They're dealing with higher frequency modes, they're testing smaller objects, and they might only be interested in what happens to that accelerometer in the high frequency range, which is a lot of our customers. So in those cases, oftentimes just a high frequency calibration will get you what you need for frequency response. The other thing we can check in a sensor is actually the resonant frequency itself. For most of that low frequency portion back there, we're checking whether the sensitivity falls within these tolerance bands. But if we keep going past the high frequency tolerance bands, past the 3 dB high frequency tolerance, and keep going, and put very high frequency energy into our sensor, we can actually see, as in the bottom graph there, at what frequency do we achieve a resonance. And that's, in this case, a ratio of the sensor under test output to the reference standards output. And you can see we express it as a gain, and that peak there that you see is about 25 kilohertz or so. And we can give this value, this frequency, as a resonant frequency as a form of another calibration method. So it's going to give you the frequency that this resonance occurs, and it gives you a little bit more information about the quality of the mounting for the sensor. Excuse me. So that resonant frequency is going to be based on step sign again. So it's the same method that we'd use for frequency response, just up to higher frequencies. And we can do this method as long as we are below the resonance of our reference sensor. And in the case of like our air bearing shaker here, our resonance sensor has a frequency of about 70 kilohertz, so very, very high. And we can test resonances of test sensors below that range. So we typically limit that to about 50 kilohertz as a maximum resonant frequency that we do for step sign. So additional information that you get out of your sensor. Do you need to do this for a recalibration? Maybe, not necessarily. Oftentimes, if this resonant frequency shifts enough, you're going to see it in the low frequency data as well. So you'll see those frequency response bands get clipped when your sensitivity is pushed down enough or up enough due to a shift in the resonance. So they're really kind of hand in hand, frequency response and resonance. You're checking either the low frequency or the high frequency portion of that sensor's performance. Yeah, so you can see that combined plot here again with the low frequency having your limits in it, 5%, 10%, 3 dB. Those are not fixed again. You know, you could have a 2% limit, you could have a 15% limit. Different manufacturers will have different values there for your sensitivity deviation. But ultimately, it's going to get pushed up to that amount of resonant frequency at some value there. So what if you are testing things that vary quite a bit in amplitude? These types of tests, these people doing these tests are then concerned about not just how the sensor changes sensitivity with respect to frequency, but how does that sensor change its sensitivity with respect to test amplitude? And that's where linearity testing comes in. And we can do that in a couple different ways. The simplest way is just keep that sensor on the shaker and do step sign tests, but instead of changing the frequency with each of those sine waves, change the test amplitude with those sine waves. And up to a certain level, not pictured on this plot here, it's going to be way down around 40 Gs, 40 Gs. That's about the highest that we can test on the air-bearing shaker. It's a limitation of the continuous nature of the test. You're going to be vibrating a payload on a shaker continuously with increasing levels of test amplitude. And thermally on that shaker, there's going to be some sort of limit that defines how warm you can get based on the force that you're generating with the coil, which is ultimately a factor of how much current you're running through that coil. So there is a limitation if you're doing step sign as to how high you can achieve in an output. But with different methods of excitation of that sensor, we can extend that up to 5,000, 10,000 Gs. The method is typically the same between these though. When you were defining a linearity, it's ultimately going to be expressed as a percentage, as you can see there in green. And we're just going to look at what is the sensitivity at each of these acceleration levels and fit a best fit straight line through that data, usually zero-based best fit straight line, and look at which point has the furthest deviation from that line, and that value divided by the full scale range expressed as a percentage is going to be your linearity for your test. So this is often spec'd as well for most accelerometers. You'll see 1% as being a pretty typical full-scale linearity or non-linearity, nominal linearity for a sensor. In reality, with things like quartz, the linearity is going to be much, much lower than 1%. So if you do some of these tests up to the full-scale range on a quartz-based sensor, you're going to get much less than 1%. Don't worry, that's normal. You get very linear response out of those type of sensors. So what if you want to go higher? This is the other means of excitation for linearity. It's the same kind of concept with a back-to-back type calibration. You have a test sensor on the top here, and you have a reference accelerometer on the bottom. They're mounted in the back-to-back configuration, and you make that same assumption that the acceleration level that those two sensors see is the same. The difference here is instead of shaking these two items continuously with a sine wave, you excite them with a shock impact in a half sine pulse. So it's a shorter time duration event, and so the total amount of energy that you put into it in a pulse versus a continuous sine wave is going to be less. So there's less heating, less overall energy that you'd need to input into the sensor. And we put a little bit of mitigating material in between our sensors and that impact material, the shock impact or projectile, and we call that an anvil. It's a thing that you're hitting, kind of makes sense. And then right at the tip of that anvil, right where that shock projectile impacts is actually a little bit of mitigating material. And we can use that material or change the thickness of that material or the type of that material to achieve different pulse widths. So we have this half sine pulse. We can have a higher impact velocity to get a taller peak, more acceleration out of our sensor stack. And we can change the material that we use there to change the width of that pulse. So in changing mass of the anvil, the type of tip that we use for the shock impact, we can shape the pulse to contain a frequency response or a frequency content that we're interested in exciting our test sensors with. And this is kind of what the software looks like to do something like that. You can see an image of the pulse on the right there. We have two outputs, one from the reference sensor, one from the test sensor. And that's a typical kind of shock pulse that you'd see in one of these shock linearity calibrations. So this type of thing is defined in ISO 16063 part 22. Part 21 is the vibration portion, part 22 is for shock. And with this type of excitation, we can get up to 10,000 Gs, 100,000 meters per second squared, and get linearity up to these higher test levels. So if you're doing the type of testing where you have high energy impacts or you're not really sure how hard of an impact you're going to have, and there could be more variability in your test, that's where people become interested in getting a shock calibration done on their sensor. So the last few things here on calibration types, we have a few, I wouldn't call them quite specialty, but a little bit more rare methods of calibrating a sensor. One of them is electrically with bias voltage. And we can see here a nice little diagram of an ICP sensor on the left and an ICP constant current signal conditioner on the right. So if we kind of come in here and look at the left here, it's a dotted box that really kind of represents our sensor. We have capacitance and a resistance. We have a crystal in here with some charge output and an ICP circuit, which often is a MOSFET or JFET inside the sensor. And then outside of the sensor, we have a 2-conductor cable, and that is connected to some form of signal conditioning, constant current signal conditioner, ICP or IEPE signal conditioner. And what this signal conditioner is doing is applying some constant current with a current regulating diode, and it has some voltage power supply, usually between 18 and 30 volts. 24 is pretty common that you'll see on most ICP signal conditioners. And you have a VM here, just a voltmeter. It's measuring across the input side of that signal conditioner. And so what you can measure there is that thing that's circled is approximately 10 volts. So on the sensor side of a signal conditioner, when you plug that sensor in, it's going to bias out to approximately 10 volts. It could be 8 volts, it could be 14 volts. It depends on the sensor that you plug into it. And this is something that the conditioner can measure. If you connect your sensor to the left side of this conditioner and on the right side on the output, if that's where you connect your meter to measure this 10 volts DC, you're not actually going to see it. Between signal and ground, you're going to see 0 volts because you have this decoupling capacitor in there. The output of most ICP signal conditioners is going to be AC coupled. That means only AC signals are going to pass through, and it's going to knock out any DC signals with this decoupling capacitor here. So don't be that person that connects to the output of the conditioner, tries to measure DC, and is confused when you see 0 volts. If you want to measure this bias voltage, this 10 volt approximately characteristic of a sensor, what you can do is you can put a BNC between, or really on the output of the signal conditioner here, and connect your sensor to one end of that T, and then connect your measuring device to the other end of that T. So you'll have the ability to power your sensor with the constant current, but also measure on the input side of that signal conditioner, and you can measure the bias voltage. So, why is it important? What is this bias voltage? It's another data set, another data point that you can get on your sensor, and it provides a little bit of health information as to how that sensor is performing. And kind of the advantage that you get most of the time is over time you can trend the performance of that sensor with respect to bias voltage. And what you can see sometimes is damage to that sensor, not on the bottom, but usually around the weld point, or if you have an epoxy sealed accelerometer, you can detect damage to that epoxy. What happens is you'll get humidity that will enter the cavity of the accelerometer, and it's going to change that bias voltage with proportion to the humidity. So I've actually done that kind of recently. It's just even looking at laboratory humidity environment. So oftentimes during a calibration, we're going to record temperature, humidity, and pressure. If you plot that versus bias voltage, you can actually see a difference there between the sensitivity or the humidity in the room and the bias voltage output that you're getting. It's kind of neat. So they're proportional to each other, and it's a good indicator if you have damage to that hermetic seal on the can. If moisture's getting in, the sensor's going to effectively breathe, and it's going to over time damage the components inside the sensor. So paying attention to the structure, the seal on the sensor can be done through bias voltage measurement. Another electrical test we have on here is the zero measurand output voltage, or ZMO. This is something that can be done for a DC responding sensor, like a piezoresistive type. And a ZMO can actually be measured relatively easily. If you connect it up to a signal conditioner without any zeroing on it, so you don't want to have any effect from your signal conditioner, zeroing out any DC voltages, you want to measure those kind of as they are. You can do a flip test like this, which is having the sensor placed typically on a table or a surface plate, something like that, and flipping that sensor over 180 degrees. So the condition that that sensor sees switches between -1G and +1G. And you'll get a little step like you see down here in the plot from that -1G to the +1G. And if you look at those values, getting ahead of myself. If you look at these two values relative to each other, you can typically add them to each other, or take the positive and take the positive value, subtract out the negative value to get close to the zero value. And additionally, between these two, you can actually put the sensor on its side to kind of just directly see a 0G condition and what that offset voltage is. So ultimately what you're seeing here is how much output does this sensor have when it should have zero acceleration. So it's a DC voltage offset that you can measure on your sensor. So it's an effect of the alignment of the sensing element inside the sensor, and kind of really just the structural alignment of the base of the accelerometer. Now one here, time constant. What happens to a sensor that has a non-DC responding output? So with a DC responding output, like the last one, if you put a step into a sensor, you see a step out. In the case of charge type accelerometers or ICP type accelerometers, if you put that same DC input into the sensor, you do not have a pure DC responding output. You have that initial step that you'll see, and then there'll be a decay in the output from that accelerometer that we call the time constant. So this is something that we can measure with that same type of flip test. Usually you have to do it in kind of a mechanized rig to flip it very, very quickly. And what this does is you can measure how long it takes for 63% of that signal to decay. And with that, you can kind of calculate what is that roll off on the low frequency end of that sensor. What's the 3 dB corner frequency for the electrical roll off of the sensor. So it's effectively doing what a low frequency calibration would do on an accelerometer just by physically flipping it up and down. And again, it's a health mainly of the electronics inside the sensor and how that roll off occurs. It's great for its simplicity and what it can do for just really flipping over a sensor, but it's not going to detect some of the errors that you'll see on an accelerometer that happen dynamically. So if there are cable resonances, connector resonances, anything that's mechanically a resonance inside the sensor, you're not going to detect it as well with this type of method, since the energy you put into it is mostly DC. And that's what you're going to be looking at, is a DC response, DC roll-off. So if there are issues at low frequency that have more to do mechanically with the sensor, that's where you're going to want to do a full low frequency calibration of that device. And yeah, here's kind of that exact same plot that I showed you from before. It's that same sensor that underwent some sort of damage. It's a great example here too. If you just did the low frequency calibration to get the low frequency roll off, you'd say the sensor's fine. If you just did this time constant test to get a mathematical approximation there of what is that low frequency roll off, again, you'd say the sensor is fine. Or if you did, like before, the single frequency point, you'd say the sensor is fine. So this is kind of to reiterate, really the most often way that we see sensors fail is up here at high frequency, is that shift in the resonant frequency into your relevant test data. So, if you're doing any one of these tests on a sensor, it's usually going to be the reference frequency, reference sensitivity test, and the very, very close second, or almost always second, test that people do is the frequency response in the high frequency regime. All these other tests that I've shown after this are kind of additional tests that people do depending on the specific type of testing that they're doing. And yeah, I think that rounds it out here for this section. We'll come back in the next part on what happens for lateral motion, so transverse motion, its effect on an accelerometer, and what transverse sensitivity calibration looks like for an accelerometer. So thank you for your time, and I hope to see you all in the next webinar.